I'm Pranati. I am the host of Under the Microscope and just finished recording a podcast with Rebecca, who is a postdoc at the University of Copenhagen in Denmark, and she is researching. So her research is about green energy, so hydrogen fuel cells, and it's more on the basic science level, where her group, like, she studies the reactions that happen in order to generate hydrogen. And so, I mean, considering the current times that we are living in, which are with the gas prices going up, it's really, really important to have green energy, put as much money as possible in developing green energy and transferring it from the lab to our cars or so, wherever. So it was a really fun conversation about her career, which started in Germany. Then she did some lab hopping here and there in Europe, and now is in Denmark. And we talked about her wishes, what she would like to see in the research environment as a whole. I also asked her a lot of questions because her research is super interesting. So can't wait for you all to watch the video or listen to the podcast, depending on where you are consuming this. So stay tuned for more details about boosting green energy, one reaction at a time. All right, bye. Hi everyone, I am Pranati, your host of the Under the Microscope podcast series, and today we have with us Rebecca I'm gonna get this right. Pittkowski, Rebecca Pittkowski, who is a postdoctoral researcher at the University of Copenhagen in Denmark, talking about boosting the green energy, one reaction at a time. And what better place to do research on green energy or alternative energy than Denmark. So, hi Rebecca, welcome to Under the Microscope. How are you?
Hi, I'm great, thanks.
Awesome. Let's so tell me everything. But let's maybe start with your research. Could you explain your research to us in super simple words, please?
Yeah, I'll try. So I work on making new materials as catalysts for fuel cell reactions or electrolysis reactions. So how to make hydrogen and how to convert hydrogen again. So basically using hydrogen as our green energy carrier. And my work is mostly on synthesizing the materials and then characterizing them with a lot of X-rays. So I'm super excited about X-rays, and I think we'll talk about that a lot. And then, of course, testing how these materials perform, if we can actually have a better catalyst for maybe our fuel cell car or for our electrolyzer.
Okay, so what kind of catalysts are we talking about here? I thought you just have the water and then you pass some current and then suddenly there is hydrogen and then you use this hydrogen to travel from Berlin to Hamburg.
Yes, that's pretty much what you do, but it depends a lot. Like if you have your glass of water where you put in your electrodes and put the current, what materials they are made of. So depending on if you have just two steel plates that you put inside, or maybe copper or platinum or nickel, depending on that, it depends on how much current you need from your socket, or like how much you need to put in and how much hydrogen you get out. So we want to make this as efficient as possible. And then basically what you would do is put a lot of nanoparticles on your electrode, because you want to have a huge surface area. So of course, we want to have as much surface as possible when the reaction takes place, and we're excited about nanomaterials, of course. And then we want to find out what materials these nanoparticles should be made of.
Okay, so the hydrogen is made or created at the anode or the cathode?
At the cathode.
And the cathode is the negative one.
Yeah, you do the reduction at the cathode. and the oxidation at the anode. So you oxidize your water at the anode and make oxygen, and you reduce your protons on the cathode to make the hydrogen.
And cathode is the negatively charged electrode.
It's the positively charged.
It's the positively charged. Okay. Positively charged electrode where you reduce your protons because the protons give the positive charge to the cathode. Did I understand this correct? Yeah. Okay. Yeah. Sorry. I always get confused with like which one is the anode, which one is the cathode, because it's like switched.
The anode, yeah, in the batteries it switches all the time, but in the fuel cell you always have to think about the anode is the oxidation. So where you have two vowels, anode oxidation and cathode reduction. So at the cathode you put the electrons into your material, and then in the anode you oxidize it, so you take away the electrodes.
Okay. Yes, this was a very quick refresher for me in electrochemistry.
But I also get confused about positive and negative, so I always have to think about where is the reaction happening. So where is the oxidation and where is the reduction?
The reduction. But this is good, like anode oxidation.
Yes.
Then cathode has to be reduction.
Reduction,
so
yeah.
It helps.
Just vowel and consonant.
Right, that's good. Yeah, thank you, Rebecca. I have probably a stupid question, but I'm still going to ask you because you're the expert here of the electrochemistry and green and everything, green energy and everything. So the hydrogen is created. It's in the liquid, in the electrolyte, the liquid where we have these two electrodes. How do you store it? Like, how does it go from being created at the cathode to running my car?
Yeah, so there's a lot of different approaches on how you would design your fuel cell for your car. So in your car, you're not going to have like a beaker of water, which you place in your electrodes. But what you probably will have is like a polymer electrolyte fuel cell where you don't actually have liquid inside, but you have like a plastic membrane, so a polymer membrane, and then you have gases flowing through. And with that, you can already make pressurized hydrogen. So that would already be at a high. Sorry, now I'm on the wrong. No. Now I got confused with electrolyzers and fuel cells, so we have to cut that.
No.
So, I mean, you put in your hydrogen. You have a hydrogen tank in your car,
right?
And then it runs through your fuel cell, but you don't have a liquid electrolyte. So you have your hydrogen running to your electrode, and there it's being, because you have hydrogen and oxygen that react together and make water in your fuel cell.
Right.
The other thing is, of course, the electrolyzer where you make the hydrogen at your cathode.
Right.
So it's turned around and.
So in reality, like when in the real life examples, it's the other way around.
Well, it depends on what you want to do. So first, if we want to have it like as a hydrogen economy, so we start to have green electricity from solar or wind. And then to store that, we produce the hydrogen. So we use the electricity to drive our electrodes in our beaker of water, which is not a beaker of water, but
right. Yeah.
We have our water to make the hydrogen, and then we store that in a pressurized tank, which we put into our car, and then we use this to power our fuel cell. So you have your pressurized hydrogen car in your fuel cell, pressurized tank in your fuel cell car, sorry. And then you use it to power your car through this fuel cell, where you basically have hydrogen and oxygen that recombine to water and release the electricity again. And then you have water that comes out of your exhaust, and no CO2, but water that comes out of the car.
Oh, that is so cool. That is so cool. I always wondered. I'm so glad you're on the podcast today, Rebecca.
Well, it sounds a little bit confusing how I tell it, because I'm also a little bit confused.
You're doing the work in the lab, right? You're not one who is transferring this from lab into the car. So no, this is really helpful, and this is really, 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 really fascinating. And considering the times that we are living in, where suddenly the gas prices go up by 34%, which is quite a lot. It's really good to be informed about um, alternative energy sources, because it's, I think, very, very important. So, Rebecca, how did you end up being this renewable energy X-ray scientist in Denmark as a postdoc, where you are at the University of Copenhagen? How has your journey been like?
I think the first time I got excited about fuel cell cars was actually in high school. And I had a really nice physics teacher who was talking about fuel cell cars, and like you can like power your car with hydrogen and it just comes water out. And I was so amazed. I thought that's really exciting. So I think I was 15 at that point.
Mm-hmm.
But I didn't really think about I want to work with that, but it just got me really excited about energy, material, like how can we work? Because I mean it's 15 years ago maybe, but it was already a point that you were saying we shouldn't use fossil fuels for 20 years at that point. So I mean it's not a new point, right? But then you were saying like, yeah, we can make fuel cell cars, and I was like, okay, why don't we do that? Okay. And then I didn't really think about it too much and started studying chemistry just because I was excited about molecules and rearrangements and atomic structures and all these. How does the structure of the material function? So I studied chemistry in Dresden in Germany, and then I moved to Prague to do my PhD. And there I actually started working on electrolysis, so how to make efficient oxygen and hydrogen from water. So the reverse of the fuel cell, what we talked about before, that we need to store our electricity that we make into the hydrogen. And then I did my PhD in Prague in Czech Republic for 3 years in a nice European project. And then I moved to Switzerland for a short while, and then to Denmark. And now I also work on the other side. So also the fuel cell side, kind of. So a lot of hydrogen on all sides for me. Making hydrogen and converting hydrogen.
So your research and your team's research is extremely important for us. It's what you described is a very typical traveling scientist kind of a career, right? You start in Germany, then Prague, then Switzerland, then now in Copenhagen. It's really cool. So, what is your experience like in terms of people's attitude towards green energy in the different countries? So, in Czech Republic, in Germany, in Switzerland, in Denmark, are there any differences, like stark differences, where I'm assuming that in Denmark, people are like, yes, green energy, we have it, we use it, lots of funding, yeah. But I'm curious how it is like in Germany, Switzerland, and Czech Republic.
I think there's quite a lot of funding, because of course there's a lot of European funding, but also the individual European countries put quite a lot of funding in these topics. So I think from the funding side, we're at the right topic at the right time, kind of. And I think also if you talk with people about the work that you do, they're always really excited and interested, and you're like, okay, that's super cool that you try to make it more efficient and try to actually, make fuel cell cars, or maybe stationary fuel cells, make them that we could actually use it. From living in these different countries, I think probably Denmark is the most advanced in having a low carbon footprint, due to, as we talked before, that there's a lot of cycling going on, that at least in Copenhagen, no one uses the car. So that was definitely different in Prague. I think there was a lot more car driving in Prague, but I think from people's attitude, it's been overall super positive in like all the places I've been in. Just every country is trying to do their own solution, kind of. So there's a lot of wind power being installed here, and then in Switzerland there's a lot of water power, like hydropower. So I think that's also like a very good point to see, like, how can you actually go towards green energy sources with what you have available. Like it doesn't maybe make so much sense to have as much solar cells in Denmark than in some other countries. So I really to find like a local solution, and I think just that we all try to work on own small solutions and figuring out what could be the possibilities and be as creative as we can be.
That makes sense. It's nice to hear that all countries are trying their best to invest and support and find solutions for green energy in order to then, of course, lowering the carbon footprint, because I think it's very, very important. Thank you for sharing that. That is really useful information. Puts things in perspective a bit for me. So, Rebecca, it sounds to me that your current research is, of course, amazing and super fascinating and super cool. But I'm sure in the past also you have been involved in a lot of interesting research experiments and research projects. If you have to pick one research project that you're most proud of, or the most fun or quirky one, could you pick one for us and explain it to us in simple words in the section we call In Other Words?
Yes. So I've mentioned it quickly before that I'm very excited about X-rays. And many of the experiments I'm doing now is with super high intensity X-rays. So if you think about your X-ray source in the maybe hospital, which everyone knows, the X-rays that we use are a couple of million times more intense. And of course, we don't have that in our lab, but we go to a large scale facility called a synchrotron, which is like a huge ring where the electrons race around at really, really high speeds. And then you take out your X-rays and you have super, powerful X-rays of really, really small wavelengths. So with that, we can actually look at nanoparticles and see how are the nanoparticles behaving. And as I was saying before, we want to have nanoparticles on our electrode to have the most efficient use of the current that we put in. So what we tried at this experiment was to see, can we use the X-rays to look into our cell where the electrochemistry is happening, and can we understand how the atoms rearrange during the catalysis? So how does the structure of the nanoparticles actually look while we do the experiment, and not before or after, but to understand how does the structure change while the catalyst is running.
Oh, wow. So do you have like movies and stuff, like videos where you see like the atoms are moving?
No, it's not like a microscope.
Okay.
So what we've been doing is actually X-ray scattering experiments. So then we're not in real space, but in reciprocal space, right? If you have your diffraction pattern. So we're not really
basically a graph.
We're not having movies, but I think it's possible to do X-ray imaging, but that's not my my experience. I'm really more interested to see, like, to solve how the atomic structure looks, like how are the atoms arranged in your nanoparticle while it is reacting. So how does the active structure look like? Is it much more ordered or maybe disordered than what you have before? Do you have dissolution of one of the active components?
Oh wow, that is so cool. I have so many questions. Oh my first one, what is the resolution? Because I remember for X-rays, what is it, not footprint, what is it called, the spot print or something, I don't know, I forgot. Wow, I can't believe I forgot. Like for the electron microscope, the beam, the diameter of the beam.
So that also depends which X-ray beam size you use. So you can make it down to a couple of microns. I think there's also nano focus beams, but that's more into the imaging side, right? We're not doing imaging. So we shoot at your whole lot of particles, and then you see how do they scatter. So how do they interact with the X-ray beam? And then you get an overall diffraction image of your, like, the whole sample. And then you Fourier transform, do a lot of data treatment, and then you get an information of your average atomic structure of the nanoparticles.
Okay. All right. Second question. do X-rays work well in liquid medium? Because for electron microscopes, that's a no-go because of the vacuum and everything. Don't you need vacuum for
No.
these? Oh, really? Oh my God, that is so cool. Oh
I
my.
think you can think about it exactly as your X-ray in the
In the
hospital.
labs. Yeah.
If you want to X-ray your hand, you also don't need to put your hand into vacuum, thankfully.
True. Yeah, you're right. Yeah.
So it's a super cool technique where you don't have to, like, you can really look into a reaction environment without needing to change it.
Wow, that is so cool. That is so cool. Oh my God, that is so cool. Okay, third question. You mentioned the X-rays are like million times faster than when we are like X-raying our hand or whatever. How fast are they? Are we talking about speed of light, or are we talking about flash speed? Are we what?
I think it's not speed of light, but it's coming close there.
Ah, okay.
So you have the electrons that race around, and then they make the X-ray. So the
Right.
particles are the electrons in the.
Right, electrons are the ones who are like going around.
Yeah.
And not the X-rays, right? Yes, of course. Oh wow, that is so cool. So how many rounds do the electrons have to do?
I have no idea. I don't work with how to create the synchrotron.
That question I can ask our previous, like one of our previous curators or one of our previous guests, because I think she is an instrument scientist at the Australian donut, so synchrotron in Australia. So I could ask her that, like, is it 100 rounds? But yeah, oh, this is so cool. And so which synchrotron do you go to? Have you been to like several, or is it like one favorite, or?
Yeah, so we try to go to the synchrotrons that are close to us, of course, and from Copenhagen, that is in Sweden, Lund, which is just 2 hours from here. And they have the Danish beamline there, so Denmark has some dedicated beam time there, so we try to go there a lot. Then Hamburg is also a really close synchrotron at Daisy. And then I think my favorite one is the European synchrotron in Grenoble in France. I think they have the best beamlines, and it's also beautiful to go to the Alps.
That is so cool. That you were frozen there for a bit, but I think I understood what I meant. What was the first one? You mentioned Hamburg, the Daisy. Then the first one is?
It's in Sweden, Max 4 in Lund.
Ah, the one in Sweden.
Yes.
Oh, that reminds me. One of our previous guests, I think Marjorie, her name was. She also like the freezing of water, and she used X-rays to study the freezing of water, like what happens to the water. That was also cool. Okay, and yeah, well, I was gonna ask you, do you have like a favorite synchrotron? And you already answered at the Grenoble. Yeah, it's really beautiful. Yeah.
But
so which one? Yeah.
Because we're applying for beam time, right? We're not beamline scientists, but we write a proposal and then we apply. So we apply at different synchrotrons to hopefully be able to make the experiment.
Okay. So, and which one will you be at in the first week of October?
In Daisy in Hamburg.
Ah, in Daisy. Ah. It's a nice one. I like that campus. It's really cozy.
Yeah.
Very nice. All right, awesome. So speaking of beamline and everything, it's very clear to me, Rebecca, that you really love the research part of being a scientist. What else do you like about being a scientist?
Yeah, I love the traveling, and because of all the synchrotrons, we actually do travel quite a lot. So it's quite busy. And I love that it's such an international environment and that you can discuss a lot and you have the freedom to focus on your own projects and be creative.
Nice. Yeah. So traveling, international environment, and independence to let your burst of creativity just True. Yeah, you're right. I remember that as well. In my past life as a scientist, I also all three of these aspects. So it sounds to me, Rebecca, that your research experience has been wonderful, and I hope it will continue to be wonderful, of course. However, if you had three wishes to improve your research experience, what would you ask for? And I'm not promising anything.
Yeah. So I think it would be nice to have more value for the time that you put in, because it's a lot of own motivation that you put in, and it's very much pushing yourself, but there's very little reward from outside, and you don't put in your hours, you just work a lot. And I think sometimes that would be nice to have. I mean, we do have flexible hours, but it would also be nice to like see how many hours did you actually work, and to maybe take a day more off or something.
Right. Yes.
And yeah, then I think that papers, like how papers are ranked as an importance is sometimes a bit too high, because it takes a lot of time to perform the experiments that we do, for example. And it's very hard to like push out paper after paper if you want to do really exciting, really cool science with like trying absolutely new things, trying new experiments. If you apply for beam time, it takes maybe 9 months between writing the proposal and actually performing it. So it's not fast science that we're doing. It's and I think sometimes that you're not seeing how much work goes into which work. So you just see, okay, this person has, I don't know, 50 papers and this person has 10 papers, and then you're like, he's more successful or she's more successful.
That should not be the matrix. And if if it takes 9 months to even perform the experiment, then writing like data analysis, writing it up and publishing it, it sounds to me easily 2 to 3 years for it.
Yeah, it takes a while. But it's really cool experiments, and I love that.
Yeah, of course. But yeah, I feel like there should be a field on the scientific papers as to like from conception to publishing. How long did it take? But yeah, sorry, go on.
I think I had a third wish, right?
Yes, you should have the. So
yeah, then I'll just wish for more money in research.
It goes against what you said earlier for the first answer, where I was asking you all kinds of questions, and you mentioned the renewable energy research is funded quite well, but you want money, right?
But I think I'm very much on the fundamental side.
Mm-hmm.
So we're quite far away from like real applications.
Mm-hmm.
And I think funding fundamental research and having like a continuity of being able to run experiments that take a long time, being able to know that you can plan for your future. So I think some fundamental funding in science, that's
right.
That's something I would love.
that makes sense.
And it's not personally for me, but just for like a continuation of.
So if you had, okay, I have like a tricky question for you. I just thought about it. Let's say you have access to, I don't know, X million amount of money, X million euros. Like, let's say 1 million, just for making it simple. 1 million just for you, Rebecca. Do whatever you want with it. It sounds a bit like Nobel Prize, but never mind. You can you can't do both, okay? So you can either pay your salary for certain number of like until the money runs out, or you can buy an instrument or a bunch of like instruments or labs or whatever. How would you spend that 1 million?
That's a tricky question.
I know.
Yeah, I mean, I really would like to have one X-ray instrument for the lab where you could measure X-ray absorption spectroscopy with. So maybe I would go with that, because.
So not paying out the salary or like travel expenses or all of that. More instrument.
If I get really a lot of money, I really like that instrument. But then if I don't have a continuous contract, what should I do with the instrument?
Yeah, exactly. Yes. But thank you for candidly answering, like honestly answering that question. It is a tricky one. If someone were to ask me that question, I wouldn't be able to answer it either. Be like, "Ugh, everything. Can I have two? 2 million?" This sounds yeah, it makes sense. Sorry for the mean question out of nowhere. Um, one thing I definitely want to learn from you, want to ask you is before I let you go, Rebecca, because this has been wonderful and I feel like I could talk to you for hours and ask you all kinds of silly and crazy and stupid questions. But at some point, I have to let you go. But before you go, could you tell us what can the followers of the Real Scientist Nano Twitter account expect in the week that you're taking over the account, which is the first week of October 2022?
Yeah, so I will be at the synchrotron in Hamburg. So I will try to give the followers insight in how does it look in such a large facility. In DAISY, you can actually not see the ring because it's underground. So if we were at the ESRF, you could take pictures around the ring, but we'll just have to do with like a short part of the ring.
The panorama.
Yeah. Yeah, but we can like see some pictures of the experiments and how does it look with all the computers and screen. How do you like set up your experiment? So I will tweet about that, and then of course, if we come back to Denmark, I will also talk a little bit more about my science here in Copenhagen, and of course a little about green energy and transitioning to other fuels and what we do there and what I think might be important.
Okay, all right. That sounds really cool. Oh my, I can't wait to read all your tweets and look at all the pictures and images and everything on the Real Scientist Nano Twitter account. Thank you very much, Rebecca, for enlightening me. I learned a lot today, and it was really nice to meet you. And yeah, thank you very much. We would love to have you again on the podcast and on the Twitter account as well. So thank you very much, and looking forward to having you on Real Scientist Nano.
Yeah, I look really much forward to it.
Awesome.
Thank you for listening. This is Pranoti, host of Under the Microscope. To know more about us, visit our website, thesciencetalk.com, and follow us on Twitter at realsci_nano.